robot planners for group reconstruction. This project is motivated by a rise in applications of UAVs in cinematography and reconstruction. And these are problems in which you have multiple robots and you have maybe single or more targets that you'd like to have cameras oriented around to capture them in 3D. So recent advancements have produced planners for pose reconstruction of single targets. And we are interested in developing cinematic planners for the multi-target case. So we'd like to represent this problem focusing on a simplified 2D model where we have a grid environment and polygonal targets, as well as a 2D camera sensor for each of the UAVs. And for cinematography, we desire a couple outcomes. We would look like view diversity, coverage, and large target size for aerial reconstruction and filming. So view diversity is intuitive. This means that if you have a group, like on this figure in the right, of targets, that you would like your cameras distributed evenly around them to capture the best information that you can from multiple angles. And we'd also like coverage. So ideally, there should at least be one robot viewing each target or one or more robots. And we'd also like large target size. So if the targets are too far away, we kind of assume that they'll perform poorly on whatever metric we're interested in, whether it be just cinematic quality or reconstruction. We would like them to be relatively large on the sensor. And here in the left, you can see our target model, which is just a simple hexagon. And then you can see our UAV model, which is a view-limited camera that can see up to a certain distance. In order to do this, multiple UAVs must be able to coordinate in position and orientation. And you can see on the right here a mock-up of a simulated environment that I would like to develop, where you have multiple competing concerns. So on the left, you have a large group that's surrounded by 3 drones for good view diversity. Then you have a smaller group covered by 2 drones, and then one group covered by 1. And what we'd like to see is how this system responds and changes to targets and merging and switching in groups, as well as with obstacles or inter-target constraints. So existing methods often solve some of these challenges, but possess one or more weaknesses that we'd like to address. So formation-based planners typically struggle with cluttered environments or groups splitting and merging. Learning-based methods tend to struggle to match performance of formation-based planners in canonical or simple cases. And yeah, we would like to develop a new perception planner for multi-UAV, multi-target tracking for cinematography or reconstruction. For our purposes, they're fairly similar. So we approach this by applying a couple techniques, but the biggest one is sequential greedy algorithms. So we sequentially plan while considering the paths of prior robots. So you can see here on the right that we have a robot 1 that has produced a plan, and it's a receding horizon problem. So we look at up to like maybe k steps ahead in time. So let's say the first robot produces this plan, maximizing some objective, and it gets to over here. Before this plan is executed, we first send that plan to the second robot. And, well, in this case, for our simulator, this would just be changing it in memory. But we let the second robot know what the first robot's planning on doing, and then we take that into account when we're doing each step of the forward for the next robot. And then you can just continue doing this for multiple robots. And this requires that your objective is formulated in such a way that it is affected by the state of other robots. And but another big benefit of sequential greedy algorithms is that they give nice performance guarantees if you formulate your problem correctly. And I'll talk a little bit more about that later. But the gist is that we can get guarantees that we'll have performance within half of optimal as a baseline. So also, we need to use a single robot planner to do this because sequential greedy algorithms really just cover the actual coordination of information across them, not so much the actual optimization step. And so for that, we're using value iteration, which produces optimal plans. So our filming objective, we desire a couple things out of it. So we'd like it to be submodular and monotonic, and these are actually the two properties, along with some others for how your constraints work. But these are the two main properties that determine if you can get a bound on your suboptimality using the sequential greedy algorithms. And so submodular just means that you're having diminishing returns, and monotonic means that it's always increasing. And so we would like our filming objective to have these properties, so that way we can get a bound on our suboptimality. We'd also like to promote desired behavior and avoid undesirable behavior. So on the right here, we have some behaviors that can reduce reconstruction or maybe cinematic quality. So you can see here that we have 3 that are the opposites of the things that we're shooting for from the previous slide. Targets too small, poor view diversity, or poor coverage. But this one also includes poor adaptability. So what I mean by this is you can't adapt or respond to cluttered environments or maybe more challenging situations like groups splitting and merging. And so we'd like to have something that is capable of doing that. And on the left here, I have a graphic that kind of hints at how the objective is currently formulated. So our targets are discretized into polygons, so that way we can compute, we can reward views that produce coverage across multiple faces and reward against faces that have already been seen by the other robot. And we also reward for the distance from the UAV to the object, so that we can reward robots getting closer to them. And so some of the experiments we'd like to do involve comparing against a adaptive formation planner. So by this, we mean something similar to Cherie's work, but adaptive formation planners should adapt to obstacles by rotating and scaling their formation, but still be locked into that formation. So typically, I mean, these have been developed for single target tracking, but we're also interested in adapting them to a group. But for the purpose of comparison, we'll just say that the formation is centered around the centroid of the group. So we're expecting to match in simple or canonical cases, and we're looking to outperform in cluttered environments and group splitting. So in canonical cases, you have just no obstacles, no splitting, everything is concentrated, and you can't really get much better than just being in a circle around your group. But in cluttered environments where that formation may be unable to adapt to the situation, or when groups are splitting and merging and the centroid is now way off the actual distribution, then we expect to exceed in performance. Yeah, so in conclusion, greedy planners provide some compelling benefits. They can produce bounded suboptimality, can be modified to account for occlusions and collisions, so we can update our objectives to reward for exposing multiple target faces from different sides. It's formation free, so we should be able to adapt to more scenarios than previously available for the purposes of optimization. And it can also work with any single robot planner. You have to be a little bit careful if you want to maintain the suboptimality bound, but it can in principle work with any single robot planner, so you can utilize advancements in single robot planners to do this. And thank you. That's the rest of my talk, and here are my references.